Hello students, in this video I will discuss some examples of Cauchy's integral formula for derivatives. It is the part of complex analysis mathematics paper 3, Karnataka University, Dharwad, BSc 6th semester. So now we shall see the examples of Cauchy's integral formula for derivatives. Before that we shall see the statement of Cauchy's integral formula for derivatives. So if f of z is analytic within and on a closed contour C and A is any point lying inside the contour C or inside the domain C, then for n values 1, 2, 3, etc. is the nth derivative of f of A is equal to n factorial divided by 2 pi I into integration of f of z divided by z minus a whole to the power of n plus 1 over the closed contour C, or else it is integration of f of z over z minus a to the power of n plus 1 over the closed contour C equal to 2 pi I by n factorial into fn of a there, where n which indicates that is the nth derivative of the function at z equal to a there. So that is what it is, the statement of the Cauchy's integral formula for derivatives. So now we shall see the problems based on that problem, Cauchy's integral formula for derivatives. First problem, that is show that first integration of 1 over z minus a over the closed contour C is 2 pi I, we can show that. And another one, integration of 1 by z minus a to the power of n over the closed contour C, that is 0 for n is 2, 3, 4, etc. Where C is the circle, equation of the circle in the modulus form, that is modulus of z minus a equal to r, where a is the constant, it is the center of the circle there. So now we shall see the solution of this problem. So that the contour C, that modulus of z minus a equal to r, which represents a circle centered at A and radius r units that. On the circle, as we know that equation of the circle, z minus a equal to r into e to the power of I theta. As also we know the domain of circle, it is 0 to 2 pi, that is the theta domain there. And differentiate of this dz, and r is constant throughout that in the circle, so that the radius is constant there, and only theta is the variation, so that phi can differentiate with respect to theta here. So then e power I theta, it means what, I into e power I theta, that is r is constant and with respect to theta there. By taking the first problem, so we need to show that 2 pi I, so integration of dz divided by z minus a over the closed curve C, so that you can substitute dz and z minus a, which is the equation of circle. So then it gets cancelled each other for that r to e power I theta, and only I remains, and integration of d theta over 0 to 2 pi, it is a theta, and which gives 2 pi I is the results of that as we have derived. And then second results, that is integration of dz over that is 1 z minus a to the power of n over the closed curve C that. So then we have here as substitute by that dz and z minus a, then it is r into I e to the power of I theta, for it is dz d, and r in e power I n theta, it is z minus a to the power of n. So as this e power, so anyway this r to the power of 1 minus n and I is there, and then also we have that is integration with respect to theta, we can take it inside the integral sign, so that e power I into 1 minus n theta there, because if you take to the numerator, so that it becomes minus n theta into I there, so that is what there. So integrate that e power I into 1 minus n theta, that is which gives that is e power I into 1 minus n into theta divided by, this is the very coefficients of this, so that it will be divided by that. So then that is what, that is just common that term is there, because over the domain 0 to 2 pi, substitute for e power I into 1 minus n theta, theta is 2 pi and 0 there, so that then it gives, that is use the de Moivre's theorem, and which gives, that is this e power 0 is 1 and this is what, it is a even term, so that only that is the first term is also 1, and it is, if you take like this, it is also 1, the sign into 1 minus n that, so definitely this is a 0 there, and only the term of cos of 1 minus n into 2 pi, it is 1 there, and 1 minus 1, it is 0 there, it is the results of that. And in the second problem, it is in the denominator of that integral z square plus 4 whole to the power 4, where c is a circle, mod z minus I equal to 2 there. This represents a circle with center at I and radius 2 units. And consider this is 2 z square plus 4 to the power 4, and then we have simplified the factorization, z plus 2i whole square and into z minus 2i whole square. And consider this, you can take it this 1 over z square plus 4 whole power 4. So then it can be taken in such a way that, so that is what, it is the phi z that. So then it is this phi z is not analytic if the denominator of this expression of phi z is 0 there. And then we have got it from that, we have 2 points which lies, definitely it is minus 2i, it comes outside, and plus 2i only which lies inside there. So inside the circle mod z minus I. So that is what, it is the way of doing there. So then, so this z equal to 2i lies within a C, and whereas z equal to minus 2i which lies outside C there. So once which only we can find the integration, only the point which lies inside C, that's why only we can find out that results there. So then what about which lies outside, that you can take to the numerator of that integral, so that is what, it is a minus 2i comes outside there. 1 out z plus that expression, you can take it to the numerator, and then we have we can treat this as f of z, and z minus 2i whole square remains in that, where this f of z is analytic inside and on the boundary of the closed contour C. Then we have, that is what we are seeing that here. Therefore we can apply the Cauchy's integral formula for derivative by taking that 2i is the point which lies inside C, so that we can take it, that is the integral formula for derivatives. So with the help of that 2 pi I into fn of a, that it is a first derivative only, that is 1 plus 1, it is a 2 there, that is n plus 1, n is 1 here, that's why we are here 1 first derivative only we can at z equal to 2i. That results which is having 1 by 2i, 4i. So that is, and then also it is a derivative of this, it is there. So this is minus 2 by z plus 2i whole to the power cube there. So that is what that is there. So simplify that, we get it, that is the result is 5 by 16 there. And in the third problem also we can evaluate, that is the problem here, domain is e power 2z divided by z minus 2 whole cube, and where C is the circle mod z equal to 3 there. So then we can take this, it is phi z, it is not analytic if this expression of the denominator of phi z is 0 there. And then what is the point which is only z equal to 2? Anyway, this domain is 3 there. So then definitely this 2 is lies inside C that. So then now you can take it, that is this, you can treat it as f of z, which is analytic inside and on the boundary of this domain circle C, and we can treat this as f of z. Therefore by Cauchy's integral formula for derivatives, so that here 3 there, it is definitely you can n plus 1, it means what you can have that is 3 there, is 2 plus 1, so that second derivative you can find at z equal to 2 there. So then that is a value is 2 there. Just we can find out the results of that, this which gives, that is the 2, 4, that is the results, second derivative result is this one, and substitute in the above equation, which gives to 4 pi I into e square there. That results of that integration of this e power 2z by z minus 2 whole cube. And similarly, next we can take it another problem, e power 3z by z square, where c is the circle mod z equal to 1. This represents a circle center at origin and radius 1 unit, and our unit circle that. So then we can have a, that is the, this we can treat it as a pz there, and this one we can take it as it is f of z, and then ultimately this is what we have taking the first derivative of this f of z, and z minus 0 whole square, z equal to 0 is the point which lies inside the unit circle there. So now we can help with the help of integral formula for derivatives. So we could find out the first derivative at 0 here, and then we can make use of, that is the f of z equal to e power 3z, and first derivative is 3 into e power 3z, and substitute the results at z equal to 0, so that it is 3. Substitute in the f dash of 0 in this results of this integration, so that which gives, that is the 6 pi I is the results of this integration. And in the fifth problem again, it is 3z minus 1 by z cube minus z over the closed contour C, but circle is mod z equal to half and mod z equal to 2 then. For the first domain we can check it that, and second domain also we can check it. This is the, by taking this expression of 3z minus 1 by z cube minus z, simplify by using the partial fractions, we get it 1 by z minus 2 by z plus 1 by z minus 1. So these are the three terms here. Just integrate throughout on this individual expressions of 3z minus 1 by z cube minus z. So this three integrals here, so that we can check it to 1 by 1 domain there, mod z equal to half there, which represents a circle with center at origin and radius half unit. And anyway, this is what f of z, it is not analytic at z equal to 0 and plus or minus 1, but 0 is only the point which lies inside C, because since its domain of the circle is half only. So whereas this minus 1 and plus 1 which goes outside lies outside, so then we can make use of the formula for derivatives, and then we can have that is the 2 pi I into f of a, that is what there. And then this is the only, that is f of z is 1 here, so that f of 0 is also 1. So then it is 1 by z here, so that is what, a is 0 here. So that only f of 0 is 1, so that this result. Similarly, by Gauss's integral formula for this, it is the first, second and third expressions of the integral is 0. So that equation 1 becomes, so that all the three integral results, first result is 2 pi, and second results, because since this minus 1 and plus 1 lies outside, definitely these two integral results are 0 by using the Gauss's integral formula theorem concept there. And next we know that it is a 2 there, so that all the 3 points which lies inside C, just we can make use of, that is the 1 by 1 there at 0, at 1, as well as this. So that all these are 2 pi results. So both, because since it is all the points which lies inside C. So we get the results is, that is what we have got it, that is the substitute, this is 2 pi I, and 2 into this, it is 4 pi I, and it is also this. So then definitely it would be having that results, because since it is the equation 1, this is 2 pi, this 2 into 2 pi I, it is 4 pi I, and this is what we have, that also 2 pi I. So then which gives the results is that it is whole integration of 3z minus 1 by z cube minus z over the closed domain C, that is 0 there. So we have discussed in this video examples on Gauss's integral formula for derivatives. So in detail, you can refer my study materials on this session number 14. Thank you very much.